and crank this puppy out, and then we'll move on to the next page. All right, so some problems are easier than others. You know, number one wasn't a big deal because they had nice clean values, and as far as the unit circle measures, they weren't overly complicated. But now you get to this one, and things are getting a little dicier, right? In terms of actually knowing where the point plots, that's actually not the worst idea in the world to do initially before you actually start the conversion process, just to get a sense of where you ought to end up. That's entirely up to you. You could do it after the fact, you know, only if the question requires you to plot. But sometimes I like to just plot it to make sure, you know, I like to feel good about my response, right? So for number two, we have an R value of -2 and a theta value of -5 pi over 6. So 5 pi over 6 would be, and I'll just indicate it on the circle down here. So we'd be looking at this guy right here. It's unlabeled, but that's what it would be. Because if you relate it back to this one, you could see that it's two little tick marks. Well, I don't know if you can call them tick marks here, but two radii up from the x-axis. So this would be 5 pi over 6. Now I need -5 pi over 6. And we talked about this last time. The negative coterminal angle is, oh, well, actually it wouldn't even be coterminal, but the negative angle, negative version of this would just be the reflection over the x-axis. Right? You can tell I'm used to saying negative coterminal. I say it all the time in a trig class. And so just kind of like when I say negative, coterminal just comes right after it in this context. So it was incorrect, but it is a movement in the clockwise direction as opposed to the counterclockwise. If you don't like that, then you can just start counting radii. So you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then just do 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, pretend it's 10. I kind of mailed it in on the counting. So, but it's 10 in either direction. All right. And so when you're standing at the pole, let me just get rid of this. It's a little messy now. When you're standing at the pole looking at 5 pi over, I'm sorry, the -5 pi over 6, what you would be doing when you have a R value of -2 is you would be taking 2 steps in the opposite direction. So this is what the opposite direction would look like. And so I would be taking 2 steps along that path. So 1, 2. So this is where number 2 ought to plot, right? So that's what I'm looking for. When I make my conversion, what I should be expecting now is a coordinate that has a positive x value and a positive y value. If I get something other than that, then I'd start thinking that I made a mistake. All right, so x is equal to r cosine theta. Y is equal to r sine theta. All right, that's our bread and butter relationship between the x's and the r's and thetas. All right, so x would be equal to -2 cosine -5 pi over 6. And then for the y, same thing, just with a sign. All right, and so it's at this point where you kind of pick your battles. If you are comfortable with your unit circle trig, then you could probably figure this out in your head. Maybe you go to the calculator. It's a lot of different possibilities. But one thing you should probably consider is the reference angle that exists here. This is a pi over 6 reference angle, or a 30-degree reference angle, right? So based off of ASTC, all students take classes, you hopefully remember that. All trig functions are positive in the first quadrant. Only the sine-related functions are positive in the second quadrant. Only the tangent-related functions in the third quadrant, and only the cosine-related functions in the fourth quadrant. All right. So I'm looking at a a pi over 6 reference angle, so a 30-degree reference angle in the third quadrant. So for my cosine function, I'm expecting the value to be negative. And the same idea for the sine function. All right, so that's good news actually, because in each case we have a -2. So -2 multiplied by something that's negative is going to give us a positive. Right, so that's good news. Now, all I would need to know is what the cosine of pi over 6 is, and that's going to be radical 3 over 2. And the sine of pi over 6 would be 1/2. All right, so we're looking at -2 times negative rad 3 over 2 is going to be positive radical 3. And get an equal sign in here. -2 times negative 1/2 is just a positive 1. All right, so my coordinate would be, so I'll just use therefore, my coordinate final answer would be radical 3, comma 1. All right. Now, in terms of the accuracy of that, we're just estimating when we plot radical 3, comma 1, but that point that I plotted there was pretty precise. It's along a line and on a ring. So that point I'm confident about. Now it's just a matter of saying, okay, well, does that amount to about 1.7-ish, comma 1? So let's take a closer look. If I were to start off at the origin and work my way over, it looks like I'm going to fall just short of 2 units away, but it does look like I'm going to go up 1 unit. So this would be less than 2 and going up 1. Well, 1.7 is less than 2. Let me clean that up a little bit. So less than 2 and going up 1 unit. So I'm pretty confident that that value is correct. And by pretty confident, I mean I'm extraordinarily confident because it is correct. Right. So, there's some unit circle skills involved there, but there's no reason you can't go to the calculator and do the computations there also. There's nothing wrong with that. You could use the Desmos calculator. You could use a graphing calculator. It's up to you. If I get I'm going to get the Desmos calculator out. Statistics here. Get rid of all that. I tend to work off of the same one, so I just delete. So if you had something like, I'll just do the cosine one. So cosine, I go to my functions, my trig functions, cosine, -5 pi divided by 6. It gives me that number, all right? Now, I wasn't always, well, I was always good at math, but I wasn't always a good math student because I was extraordinarily lazy. I'm still kind of lazy. What I do is I work hard to be lazy, right? So it's kind of a tough life to live when you desperately just want to not do work, but then you find that you have to do more work in order to do less work later on, right? And so when I was a student, I didn't buy into the whole unit circle thing. They said study the unit circle, and I said, I'm busy. I wasn't really busy. I just didn't want to do it. So I didn't study it at all. It wasn't until I became a teacher where I was like, all right, probably got to get to know this unit circle. It seems to be coming up over and over again, right? And the higher level courses I taught, the more and more it was relied upon. And so how did I get through the earlier years of mathematics in order to get to a point where I could even tackle the more complicated stuff? Calculators played a big role. And so I have this decimal value here. And so for those of you who are just like, it's on my list of things to do, this unit circle, I just can never remember it. I never have time to, whatever. For a couple of questions here or there, you can get answers in the appropriate form without having to actually know the unit circle. But if the object of an assessment is to produce the unit circle, then you got to know it, right? There's no way around it, right? So I got this decimal value. Now, one thing I did remember about the unit circle way back when I was kind of like half paying attention in class. That's not even true. Like 10% paying attention in class was that all the answers were the square root of something. And this is what goes on inside my head. So I type this value, I type the cosine of -5 pi over 6 into my calculator. And then I say, all right, well, it's the square root of something. So what is it the square root of? And so what I would do is I would take this value, let's see if it'll let me copy and paste. Oh, it would have been nice. All right, well, I'll just type it.
I mean, can't you just eyeball it? And you can see that's square root of 3 over 2.
You could eyeball it. I'm just trying to give the people who have no sense whatsoever about the unit circle some way to get questions right.
You're so nice.
I know, thoughtful. So I know it's the square root of something. So take that value, square it. Now, I just typed in an approximation, but that's pretty clearly trying to tell me 0.75. So I now know there's a negative there, so I got to hang on to that. I got to remember that. But I now know that this is the square root of 3/4, 0.75 3/4. The square root of the 3 stays as the square root of 3, but the square root of 4 becomes a 2, right? So you get your radical 3 over 2 that way, right? So for those of you who just, yeah, it's on your list of things to do, but you never quite get around to doing it, it's a little bit of a workaround as it applies to unit circle related trick. Right? It's such a non-starter to not know trig relationships that I try to give all little tools, little tips along the way, even if it brings the lesson to a screeching halt, because that's how important this material is down the line in this course. So I just got to keep hitting it hard, and hopefully, hopefully people are believing me that it's important, and then beyond that, taking some time to know this stuff. So we get into graphing polar equations, which is, not point by point, function by function, equation by equation. So some of them are simple. Numbers 5 and 6 are simple polar equations because they're constant equations, right? So R is equal to something that's not dependent on another variable, right? So R is equal to just a 3, right? What that means is R is equal to 3 regardless of theta. Regardless of theta. Another way to write that would be to say for all theta. All right? But what it's essentially getting at is the idea that it doesn't matter what theta is, R is always going to be equal to 3. All right? So with that in mind, what I can do is start plotting points 3 units away from the pole for a variety of different theta values. Right? So I'll do it for 0. I'll do it for pi over 6. I'll do it for pi over, well, yeah, I'll do it every 2 tick marks or every 2 radii. Now, there's infinitely many points that are between each of the points that I plotted, and that's how we create a circular figure. But it's kind of interesting because you can manipulate polar equations to give you non-curved equations, non-curved graphs. And so you would do that just by designating how often a point should be plotted, right? So we call that a theta step. Right? The TI-84 calculators have that built in, but the theta step I made this too thick. It looks weird now. That's how often, you know, I'm using the term often loosely. It's not a measure of time. Often we plot a point. So example, every pi over 6 radians. All right. So if I were to plot a point only every pi over 6 radians, my theta step would be equal to pi over 6. All right. And what our figure would look like, and hopefully I can do this justice, but it would be an angular looking figure. Dang it. I'm just going point to point with straight line segments. All right, so I have 1, 2, 3, 4, 5, 6, so 12-sided polygon. All right, so that's what we would get out of this, which is kind of cool. It's a 12-sided polygon. All right, now if the theta step approaches 0, right, so it doesn't actually become 0, because if that's the case, then there wouldn't be any movement from point to point. So what I say instead is I just use a limit relationship. I say if theta step approaches 0, then we're looking at a circle. All right, so I'm just going to draw a nice circle, nice shaky circle. Yeah, best I can do. All right, so if I were to make my theta step pi over 2, all right, so pi, I'll do that in a different color. I'll actually plot that also because it's kind of fun. All right, so let's say do it in blue. So if theta step equals pi over 2, I'd be looking at a point at 0, a point at pi over 2, a point at pi, and a point at 3 pi over 2. And so we would end up with a quadrilateral. But specifically, with equal length sides, diameters congruent to one another. So specifically, this would be a square. If we have a constant radius, all of these polygons that emerge from the theta step, they're all going to end up being regular polygons. So the 4-sided one's a square, 3-sided one would be an equilateral triangle, and so on. All right. So we can get a lot of different types of figures out of this, but what we're going to assume is that we want whatever equation that comes from this to be something that's differentiable. Right? So we need a smooth curve. In order for it to be smooth, we need that one case where theta step is approaching 0, the case where it leads to a circle. Right? Because otherwise we get all these corners all over the place, and we know a function isn't differentiable at any kind of point. Right? So whether it's a corner or a cusp. Now number 6 is holding theta constant at 3 pi over 4, and that's regardless of the value of r. So I'm going to get a little sneaky here. All right, so regardless of the R value, all right, so R could be 0. I'll plot a point, get a little thicker. I'll highlight 3 pi over 4, which is right here. R could be, let's say it's a positive 1, or 2, or 3, or 4, or 5, and so on. But R could be negative, which means it could be going back the other way. So it could be -1, -2, -3, -4, -5, and so on. All right, so what we get here is the equation of a line. All right, so like a line as in a linear function. So it's not a ray. And it's a common misconception when it comes to this. People think it's a ray because it starts off in one direction and ends, but it's actually a line. And there's plenty of applications of this, but if you think about circular functions, you know, you're talking about a polar graph in the real world sense. You might be thinking about latitudes and longitudes, right? So you're standing at the North Pole and you're looking off into one direction along one longitude, right? So you're standing at the North Pole and you start walking away in one direction. I mean, given enough time and resources and patience, I guess, and several lifetimes, I suppose, if you were to continue traveling along that path, eventually you would circle back around and get to the North Pole again, right? But in terms of a two-dimensional rendering of a three-dimensional idea, it's just simply a line. So it's kind of like you have to imagine that this is a way of representing one of the great circles that make up a sphere, but we're plotting it as a line, right? So it's a trip down the rabbit hole. Things are getting a little kooky now because a line isn't just a line, even though it looks like a line and it acts like a line, and in rectangular form it'll have the equation of a line. It still represents a circle if we're going in 3 dimensions.
Professor?
Hmm.
So, like, if I were to take a quarter and put it sideways and you only see, like, that line, it'd be like that.
Exactamundo.
Okay.
Very good. Good analogy. I'm going to use that from now on. So I wrote recall here below the formulas, not recall from like last semester, recall from like 2 pages ago. R equals squared x squared plus y squared and all that good stuff. The reason why I put them here, and these ones specifically, is because these are the most useful ones when it comes to converting from polar to rectangular and vice versa in terms of the equations. All right, so what we're going to do is spend a little time now just learning how to do that, because we're not limited to one technique, one method when it comes to differentiation. So here's the deal. We're learning how to convert to polar form. That doesn't mean we're going to leave the rectangular coordinate system behind. It just means in some circumstances, the rectangular coordinate system will make more sense to work with than the polar, and in other situations, the polar system will make more sense to work with than the rectangular. Part of the challenge is knowing when to use which. All right, so looking at number 7, I see an equation where if I were to work with it in polar form, it's actually not that difficult. You know, I can solve for R. I can get an equation solve for R in terms of theta. That's good news. R is the independent variable, and R is the dependent variable and theta is the independent variable. But looking at number 8, it takes a little bit more doing to do that. All right, so the goal here is to put it into rectangular form, see if there's a way that we can easily recognize the rectangular equivalent of a polar equation, and then make a determination of which one is more convenient to work with. All right, sometimes you do that even before you even think about creating a graph or getting into the calculus of it, because it just makes more sense. All right, so one relationship that we can kind of rely upon, And it's a variation of one of these rules. I just kind of scrolled and I have to scroll back. This rule here, y is equal to r times the sine of theta, can be manipulated. And we have the original form of it on a previous page, but I didn't paste it in here. Sine of theta is equal to y over r. Right? Knowing that allows me to make a substitution, because our goal here to put it in rectangular form means that we need to get rid of the r's and thetas, right? So I can't get rid of the r's just yet, but I can get rid of the theta and replace it with an expression that involves no theta, but an r. So this would be r plus 5 times y over r is equal to 0. Let me clean that up a little. All right, so it doesn't seem like we did much here, but we actually, we're making some headway because the theta's gone, all right? So that's good news, and we introduced a y instead of a theta, so that's great. Now I just want to clean it up a little bit, so I'm going to have r plus 5y over r equals 0. Now, the next couple of steps are, well, maybe next step or two are algebra based, right? So your brain might take you in a different direction than mine, but my brain is telling me, clear out that denominator. All right, so I just don't understand the concept of like honking in like a parking lot. It's like, yeah, somebody's expecting you. So what do? You just pull out in front and blare your horn. That's awesome. Like, people. Anyway, so r squared plus 5y equals 0. All right. And again, it doesn't seem like the situation has improved very much, but we're actually in a pretty good spot, because a variation of this rule, as soon as I can get my highlighter going, this rule is that x squared plus y squared is equal to r squared. All right. Now, I could have easily just copied and pasted all the things. Well, it wouldn't have been copied and pasted because I would have typed it. But I could have brought all the rules from a couple pages ago in here. But the whole idea behind this is not so much regurgitating rules as it is taking a rule that we already know and manipulating it slightly. Right? That allows us to replace, in this case, the r squared with an x squared plus y squared. So let me pause 10 seconds for station identification on that's radio network. All right, so I'm going to replace the r squared with an x squared plus y squared. And we still have the 5y, and we still have the 0. All right, now it's already shaping up like, whoa, I think maybe the polar form is probably the way to go. And I'll say it's a yes and no situation. It depends on what way you're going to tackle this, because if you're doing it on a calculator, any instance in which you can easily solve equation for one variable in terms exclusively of another, that's what I call calculator ready, right? Or calculator friendly. This one is not, but the way it's shaping up, it's actually going to be, I don't really have a fun term for this, except to say that it is by hand friendly, right? So if you were to draw a sketch of the graph without getting technology involved, it's looking like what we just wrote down, this transformed equation from one form to another, the rectangular form, is actually going to be better to draw out by hand. Right, so it's kind of like picking your battles, right? So, or at least knowing what your goals are. What is it that you want to do with this? You know, so I have x squared plus y squared plus 5y. I'm going to leave a little gap here. And I'm going to set this puppy equal to 0. All right. So the reason I'm leaving the gap there is because I'm looking at a quadratic. Right? I'm looking at something that's a second degree polynomial, at least the y part of it. I can complete the square and get it written as a binomial square. The reason why I'm not doing that for the x is because there is no middle term of the x function or the x part of the equation. So if it were x squared plus, let's say 2x, then I would look to complete the square for that part of it, but I don't need to do that because it's already just an x squared, right? So I'm going to jot down the shortcut formula for completing the square, just because why not? It's b squared over 4a. All right, because it's the same as take, you know, like you may have learned it this way. You take the b value, you cut it in half, you square it, then you divide by the leading coefficient. All right, so if you take b, divide by 2, you got b over 2. You square it, you get b squared over 4, then divide by the a value. All right, so what's the a value? In this case, the a value would be the coefficient of y. All right, so let me just tuck that in there. So this is my a. This whole thing here, including the sign, would be my b. And, you know, I should be correct about this. The coefficient of the y squared would also include the sign. Right? It's just it's positive in this case, so it didn't really matter. All right, so if I take that b value, the positive 5, square it, and divide it by 4a, right? So it's 25 over 4. That's what's going to get popped into the gap here. And if you add something to one side of an equation, you have to add it to the other. So I'm going to have my x squared plus, now this trinomial will become a binomial squared. And the whole thing is going to be equal to 25 over 4. And, you know, if you're thinking to yourself, I don't see how this is going to be easy to graph. When I talk to you about what this is the equation of, maybe you recognize it already, you'll see, right? So we're looking at y plus, when we have a perfect square trinomial, remember you take the square root of the first term, the square root of the last term, and carry down the middle sign. So 5 over 2, right? So let me just refresh our memories on what the standard form equation is for a circle. X minus h squared plus y minus k squared is equal to r squared. All right, so what I'm looking at here is a circle with the center at 0, -5/2, and a radius coincidentally of 5/2. All right, so circle with center at 0, -5/2.
Professor,
And the yo.
isn't that supposed to be -25 over 4 when you switch the sides?
No, because we want to balance the equation. So if I'm adding something to the scale on one side, I add it to the scale. Because I'm not moving from one side to the other, I'm keeping it balanced.
Okay.
So it's kind of like if I multiplied the left side of the equation by 10, I would also multiply the right side of the equation by 10.
All right.
And so the radius would be the square root of the 25 over 4, which would be 5/2. Now, and so this is kind of a weird thing to think about. We learned a little while ago, and also last week, that negative R values have meaning. Right? It's just talking about direction. So it is possible that you could have a negative radius. It just means that whatever angle you're starting at, you know, if you want to start at 0, if I had a negative radius, I would just plot my radius in the opposite direction from that angle. Right? When you're dealing with a circle and a closed circle, so infinite loop, you're not really concerned with direction because you're going to cover all the points anyway, right? But if you care about movement along that circle, then it could be a different story, right? Yeah, so that's a pretty crunchy example when it comes to the algebra of it. But really, if you think about it, the first, let's see, 1, 2, 3, like 3 steps, those were just substitutions based off of known information. The rest of it was, yeah, I know I learned that at some point. Completing the square, how does that go again? You know, so it's like old school stuff. Right?
Professor?
Yeah.
I understood everything until you started doing the b squared over 4a. Like, how are you allowed to do that?
So that's the completing the square technique?
Yeah, I know, but like, how, like, I don't know. You just lost me after that. That's just.
So that's the same as saying, take the b value, cut it in half, and square it.
So when you do that, it's like you're creating a whole new equation in the equation.
Yeah, because you can add whatever you want to an equation as long as you add it to both sides. So when I do all that work, it's for the purpose of just finding that perfect value to make a perfect square trinomial. And when that happens, it cleans up to the nice standard form.
Oh man. Okay. I'm gonna have to go over this video.
Sure. I think that if I'm not mistaken, it comes up again in the next one. If I'm wrong about that, I'll just make up another example. So, but I'm just going to write this out anyway. Take the b value, cut it in half, and square it, then divide by the a value. That's the completing the square method. And so symbolically, let's go.
I just have a quick question. I know someone just asked it, but can you explain one more time as to why when you moved over the 25/4 it doesn't become negative?
Because I didn't move it over, I introduced a new 25/4 in order to keep the equation balanced.
So the 25/4 on the left stayed, you just added another one to the right side?
Exactly. It only seems like it disappeared on the left because it factored in, when we did the factoring process, it kind of worked its way into the y plus 5 halves squared, but it's still there on the left-hand side.
Okay, I see. Thank you.
No problem. So if I take the b value, cut it in half, and square it, that would give me b over 4. If I then divide that by the a value, it gives me b squared over 4. That would give me b squared over 4a. All right, so that's where that rule is coming from. It's just a nice shorthand way of representing the completing the square technique. But let's see if I don't remember off the top of my head, and I don't want to look at an answer key because it's not big on that. It's like a rule I have with myself. Like, I should know this stuff, but I don't. Yeah, I'm pretty sure completing the square works its way into the solution, though. We'll see in a minute. All right, so r minus r times the sine of theta. In the previous problem, we said the sine of theta is the same as y over r. So I'm looking at r minus y equals 0. All right. So at first glance, it's like, whoa, this simplified significantly. But you got to remember, our goal here is to get rid of both r and theta. So the r is still there. That's got to go. Now it's just a question of, all right, in what capacity is it going to go? All right. So I can handle it a couple of ways. One way would be to add the y to both sides, which is what I'm going to do. Another way would be to make a substitution of r right now, which I'm not going to do. I'm going to move that y immediately. So r equals y, right? I can now replace, we could have done it before, but I'm now going to replace the r with the square root of x squared plus y squared. You could have also squared both sides and gone that route, but it really doesn't amount to anything in terms of whether it's not going to make it any easier to do it one way or the other. All right. So then I'm going to square both sides. So one way or another, I'm going to square both sides. And the reason I'm squaring both sides is because I don't recognize this type of function, this equation. It wouldn't be a function necessarily. I don't recognize this as a known equation. So I want to clean it up and see if I can get it into some kind of standard form to help me recognize it. Like in the previous question, I was able to look at it and say, oh, that's a circle. And this one, it's like, I'm still not seeing it. So let me square both sides and get x squared plus y squared is equal to y squared.
Professor, I have a question.
Yeah.
The square root of x squared plus y squared, isn't that like already the r squared? So
r is the square root of x squared plus y squared.
okay.
Yeah, it's r squared that's equal to the one without the radical.
Okay.
Okay, and so we end up with this. And so it actually is going to kind of clean up a lot nicer than I thought. So I guess I will be making up an example. I wonder if I change this one from something else. So I can now add or subtract a y squared from both sides and get x squared equals 0, which makes x equal to 0. And that's the equation of a vertical line. So we got an equation. We got something here. So there is a fair amount going on in this problem, but it's not the problem I was thinking of. So I'll make up one in a second. They're actually pretty easy to make up because the conic sections have a particular form. So I'll just take care of that. Okay, so we got x equals 0. Now going the other way. So I'll come back and I'll make an example after I do these two problems here.
What would the one that we just did, x equals 0, what does that equation look like in a polar graph?
It's going to look like this. I didn't time that right. This.
Okay.
Because x equals 0 is the y-axis.
Yeah.
So that's really what we're up against here. So now what we would have to do in order to get this to plot that way would be to solve, if I wanted to actually graph it, I would have to solve that equation for r in terms of theta and then go from there. But that we're going to get to that in another couple of minutes. So more on that in a few minutes. But yeah, if we wanted to go to polar form, I have x minus 4 squared plus y squared equals 16. So it's just knowledge of the basic relationships. And so I'd be looking at x squared minus 8x plus 16. That's what you would get if you distribute this guy out. Plus y squared equals 16. All right, so those two correspond, everything else is the same. Now, here, we got some nice things going on. First, I see that I got a common 16 on both sides of the equation. Let me zap those away. Because again, our ultimate goal here is to get it so that we have r's and thetas rather than x's and y's. All right. I'm also going to reorganize and make this x squared plus y squared minus 8x equals 0. Right, so I'm basically undoing everything I did in the problem above it. Right, because you can see here in this guy, x squared plus y squared plus 5y, that was the step prior to completing the square. So we're kind of uncompleting the square here, right? But we now have a relationship that we can use. That relationship is that x squared plus y squared is equal to r squared. Right? We have another relationship that we can latch onto here, and that is that x is equal to r cosine theta. So let me highlight that, and then I'll bring the 8 down along for the ride. So I now have an equation that's solved, or it's solved for 0, but it's in terms of r's and thetas rather than being in terms of x's and y's. All right, so let me just pause this real quick. All right, so yeah, it's recording now. And I can go back to this. So I have a common r and can factor that out. And it was, I mean, whether it's in polar form or rectangular form or any other kind of form, when it's quadratic, it's quadratic. If you recognize something as being quadratic, quadratic techniques would apply. So what would I do if I had a quadratic equation? I would factor, then I would set each factor equal to 0, then I would solve, right? So that's what I'm going to do here. I'd have r equals 0 and r minus 8 cosine theta is equal to 0. All right. Now, back in algebra class, college algebra, algebra 1, 2, whatever, if you got x equals 0, that was a location. And that you had to report that as an answer. If you got x equals 0, you'd say that's one of the solutions. Here, r equals 0 is a circle with a radius of 0. All right. If there's a radius of 0, then it's not a circle. Right. So there's nothing there. So this one we would disregard, and we would only go with the other option and solve that for r in terms of theta. And so we get r equals 8 cosine theta, and that would be the final answer for this.
Would we get penalized if we just left it as r squared minus 8r cosine theta?
Like everything else, it depends on the instructions. You know, these instructions said state the rectangular equation in polar form. So you would have been fine with the r squared minus 8r cosine theta. But if it says put your answer in simplest form, then you'd have to go all the way. So just follow the directions and you'll be okay.
Okay, thank you.
Put my glasses on my head and then took a sip of water and glasses fell off my head. All right, so that's that. The next one, we have x squared over 4 minus y squared equals 1. And, you know, like it's going back to the directions, it's the same idea where if it doesn't say to simplify, you don't have to. But if it does, you should, or you must. Here, you know, we could try to clean it up. We can get a common denominator. But again, like I said before, my brain takes me down a particular pathway. And it's always with the mindset of let's get rid of denominators. The only time you got to be careful about that is if you have a variable in the bottom of a fraction, because then you might have some extraneous values that you got to hang on to. So we have x squared minus 4y squared is equal to 4. Was it a necessary step? Maybe, maybe not. In the end, it was a step, and it's a correct step because it's algebraically sound. So I'm not concerned. Right now, in terms of making a substitution. And there's a couple of different ways you can go, but we do know that x is equivalent to r cosine theta and y is equivalent to r sine of theta. Right? So x squared minus 4 times y squared is equal to 4. So I'm going to do my substitutions: r cosine theta, r sine of theta. All right. Now we go down.
How did you know to use r cosine theta and r sine theta?
Because those are rules.
Rules.
X equals
Okay.
r cosine
Thank
theta.
you.
No problem. All right. And so I can clean it up a little bit. R squared cosine squared theta minus 4r squared sine squared theta is equal to 4. If our goal here is to get r alone, so solve for r in terms of theta, no, I'm not expecting something to be overly good looking in terms of a solution, but I can get r alone. I can just factor out an r squared. It's going to give me a cosine squared theta minus 4 sine squared theta. Divide, right? So it would be, change it up here, r squared would be equal to 4 over, so we get a fraction bar going here, cosine squared theta minus 4 sine squared theta. And then the only thing I could really do after this would be to take the square root. And that's fine. You know, sometimes there just isn't a nice standard form for what it is, you know, the thing that you're working with. You know, and that kind of speaks to the version of the graph that you're dealing with. And what I mean by that is, originally we're dealing with the equation of a hyperbola. And if you know how to graph a hyperbola in rectangular coordinates, what we're getting from this is that, you know, you may want to just stick with that. Because if I take the square root here, let me just go, I'll go back to purple. I'm going to get plus or minus 2 over radical, all that stuff. And it's all right to have the radical on the bottom of the fraction. We've talked about that a little bit. But if I have a choice in between graphing the original equation in rectangular form or graphing this one in polar form, if I got to do it by hand, I'm going with the original. If I got to do it on the calculator, I'm probably going with the polar. Right? So it's a matter of preference. So then let me make up an example to do another completing the square type question with you all. Let me go green for those keeping score at home. I'm going to call this 8A. I'm just going to chuck it in over here. So let's say you have r equals 1/2 sine theta. I'm keeping it simple. You know what? Maybe I don't want to keep it simple. No, I want to keep it simple because if I get a little too crazy, then I might not end up having a completing the square problem. So I don't want to get too cute. So we talked about this before. Sine of theta is the same as y over r.
Professor, and we are writing it in a polar form or quadratic form?
It's already in polar form, so we're going to rectangular form.
Oh, rectangle. Yeah, thank you.
No problem. All right, so I'm going to clean it up algebraically. We got a 2r here. Now, It's a matter of preference because some people look at this and say, okay, multiply both sides by 2r. Other people look at this and say, cross multiply. In this case, I think no matter which school of thought you're going with, it amounts to the same amount of work. So I'm going to multiply through with a 2r, and we're going to get 2r squared is equal to y. All right. Earlier, we discussed how r squared is equivalent to x squared plus y squared. Let me get those parens in there. And let me erase that. All right. So now we have an equation in rectangular form. It's just a question of, all right, well, what are the directions? If the directions are to just get it in rectangular form, we're done. If the directions are to get it into simplest form, then we get a little bit more work ahead of us. Now, it is really just a matter of preference in the next step or two, like which way do you want to go with it? Because we could distribute the two to each term, x squared and y squared, or we could divide out the two. And you know, so it ends up undoing something we just did, but that's fine. So that's what I'm going to do. I'm going to divide out the two because I like to keep my coefficients when dealing with completing the square. If possible, I like to keep the coefficients as 1. It makes life a little bit easier. So this would be 1/2 y. All right. Now we're dealing with a quadratic situation. Right? Conic sections are all quadratic equations. And so when you're dealing with quadratics, completing the square could be something that comes into play. But generally speaking, when you're dealing with quadratics, you want to get everything over to the same side. All right, so that's my next step in the process. X squared plus y squared plus 1/2 y. Going to leave a little blank to complete the square. And when I move that 1/2 y over to the left, it just gives me a 0 all alone on the right.
Isn't it minus 1/2 y?
Yeah, it would be. Thank you. All right. And so this value here, we get by performing that computation that I was talking about earlier. Let me do it in whatever this color is called. So we're figuring out b squared divided by 4a. All right, so again, the understood coefficient here is 1. So we have this guy, that's my a. This guy is my b. All right, so if I take that negative 1/2 and square it, I get 1/4. If I divide it by 4 times 1, it's 1/4 divided by 4, which is the same as 1/16. So plus 1/16. When I add 1/16 to one side, I got to add it to the other to keep the equation balanced. And so this part here, if I did everything correctly, should now be a perfect square trinomial. All right. The x squared we didn't have to worry about because there was no b term associated with the x squared. Right? If it was something like x squared plus something x, then I would have to do the same process just with the x's also. All right, but that's not the case here. All right. So I have an x squared plus a binomial squared equals 1/16. Now it's just a matter of figuring out what that binomial is, and then we'll have it. So, and again, just a little refresher, when you're factoring a perfect square trinomial, you look at your 3 terms, you take the square root of the first term, that first term is y squared, the square root of that is y. You take the square root of the last term, that last term is 1/16, the square root of 1/16 is 1/4. And then just carry down the middle sign. There's 3 signs, positive, negative, positive. The middle sign is negative. All right. So that's where my final equation in standard form would come from. So I'd be looking at a circle with center at 0, 1/4 and a radius of 1/4. And I'm going to try to bring this up a little bit. Make it a little easier. A little hair there, a little eyelash. All right. And so that's my standard form equation. But, you know, again, where's the new material in here? The first step, and that is really, oh, well, first and like the fourth step, third, fourth step. That's all, that's the polar stuff. Everything else is algebra, right? So it's just a matter of, you know, reviewing some basic concepts, you know, and completing the square. You know, it's that concept when you learned it way back when, kind of like unit circle, where you went over it, teacher presented it, and then you're like, whoa, hopefully this is a one-off. Hopefully I'm never seeing this one again. And then it just kept coming back over and over and over again. But it wasn't such a big part of every course that you were in that you can kind of like sneak your way past it without paying any significant prices. It's going to be kind of the same way here, where it's like, okay, every now and then there's going to be a completing the square problem, you know, and not just completing the square, but it'll work its way into the solution. And just life is so much easier if you know how to do it. That's why I showed the b squared over 4a formula, because when people have formulas, they tend to, in my experience, do better with some content that maybe they don't have a foundational understanding of, right? So that's a second look, and I'll take this as a typo, because I'd like to include this example in future note packets. So if you're looking for typo bonus, just send me a remind message saying on page 10, add the new example, and I'll know what that means, and you get a bonus point as long as you're the first one to get it in. All right. So first come, first serve, always on the reminder. All right, that is colorful stuff right there. Look at that. Anyway, next page we talk about what are known as classical curves. Right? Classical curves are really really important in Calc 3. And you know what? Let me stop this recording.